Before we can deal with solving systems of linear equations, we first have to understand what a linear equation is. A linear equation is one whose graph is a line. More importantly, it represents a direct and constant relationship between the input variable x and the output variable y. For example, if a certain t-shirt costs $12, then 2 would cost 2 times $12, or $24. 5 would cost 5 times $12, or $60, and 8 would cost 8 times $12, or $96. We could express this mathematically using the equation y equals 12x. Here, x is the number of shirts, and y is the total cost for the x shirts. It should be easy to see that for every one shirt we add to the purchase, the cost increases by $12. No matter how many shirts we already have in the shopping cart, one more adds $12. 4 more would add $48, 10 more would add $120, and so on. We could then say that the change in the cost, delta y, is equal to 12 times the change in the number of shirts, delta x. We can rearrange this a bit and see that the ratio of delta y to delta x, this is the rise over the run, is always 12. This ratio is called the line slope and is represented by the variable m. The slope is the rate of change of the cost function. In other words, how much the total cost changes for each shirt that we add to the cart. Notice that for a linear function, the slope never changes. One more shirt always adds $12 to the cost, no matter how many shirts we might already have in the cart. On a graph, y equals 12x looks like this. If we buy 0 shirts, x equals 0, then of course the cost, y, is also 0. If we buy 5 shirts, the cost is $60. A line through these 2 points gives us a graph showing the cost for any number of shirts. Since the slope never changes, we can extend this line as far as we need to. The other piece of a linear function that's important is the y-intercept. The y-intercept often represents a starting point or initial condition that changes the total by a fixed amount, regardless of the value of x. In our shopping example, we might imagine that it costs $3 in gas to drive to the store and back to buy all the shirts. So even if we went to the store and did not buy any shirts, it would still cost $3. If we buy one shirt, our total cost is $12 for the shirt, plus $3 for the gas, or $15 total. If we buy 2 shirts, our cost is $3 plus $24 for the shirts, or $27. And we can figure out the cost y for buying any number of shirts as y equals 12x plus 3. This shifts our graph up by 3 units. The y-intercept is given the special variable name b, so the equation for a line is usually written as y equals mx plus b. And while we're speaking of shifting the graph up, we might as well talk about transformations of the linear function. For the linear parent function y equals x, this looks like y equals plus or minus a times x minus h plus k. Well, let's put some numbers on this to see how this will work. Suppose we have the parent function stretched vertically by a factor of 12 and shifted up by 3 units. We would have y equals 12 times x minus 0 plus 3, which reduces to y equals 12x plus 3, the same as in our shopping scenario. Notice that the vertical stretch 12 is actually the slope of the line m. Now instead, suppose we apply the transformation of shifting the graph 1/4 unit left and not shifting it up at all. We would now have 12 times x plus 1/4 plus 0. But if you distribute the 12 and eliminate the 0, you still get y equals 12x plus 3. It seems that shifting 1/4 unit to the left resulted in exactly the same graph as shifting 3 units up. The linear function has the interesting property that shifting the graph left and right looks the same as shifting it up and down. So for linear functions, we usually leave out the horizontal shift h and stick with the vertical shift k. This gives us the transformation y equals plus or minus ax plus k. Now, since the vertical stretch value a is really the slope m, and the vertical shift value k is really the y-intercept b, we write the equation for a line as y equals mx plus b. M could be positive or negative. A positive slope tilts upward from left to right, which is the same as saying that the function is increasing. A negative slope tilts downward, meaning that the function is decreasing. A negative slope gives the same result as reflecting the positive line over the x-axis. A horizontal line has a zero slope since the rise is always zero, and a vertical line has an undefined slope since the run is always zero. Systems of linear equations allow us to find the values of two or more variables by considering how these variables are related to each other. For example, if there are two different price levels of tickets that are sold for a concert, and we know the number of tickets sold and the amount of money we collected, we can determine the number of each type of ticket that was sold. Regardless of what the situation is, we need to have as many equations, as many relationships, as the number of variables that we're trying to find. So how would we write equations for systems? Well, let's go back to the ticket example. Suppose we have two ticket price levels, $45 and $65, and we sold a total of 350 tickets. We collected $18,750. How many of each type of ticket did we sell? We'll start by assigning variables. X will be the number of $45 tickets, and Y will be the number of $65 tickets. Since we sold 350 tickets total, we know that X plus Y has to equal 350. We also know that the total amount of money that we collected for the $45 tickets is going to be 45 times the number of the tickets. So we'll call this 45x. Same holds for the $65 tickets. The total for those tickets is 65 times y. These added together have to equal our sum of money, which is $18,750. So 45x plus 65y has to be $18,750. Okay, so now what we have is a system of linear equations. We have x plus y equals 350, and 45x plus 65y equals 18,750. We want to find the value of x and the value of y that makes both of these true. How do we determine those values? Well, there's at least three ways to do this. We can do this graphically. Remember that each of these equations is a linear function. In other words, each could be graphed as a line. When we graph the two lines, the solution, if there is one, is going to be their point of intersection. Another method involves using algebra, and this is called substitution. We're going to solve one of the equations for either x or y, and then substitute that whole expression in place of x or y in the other expression. The third method is also an algebraic method. This is called elimination. We're going to multiply both sides of one equation by a certain number so that when we add the two equations together, we can eliminate either x or y and then solve from there. So let's look at these different methods a little bit more closely. The graphical solution is in some ways the easiest solution, but it does have its limitations. Remember that each equation is the equation of a line. To graph by hand, that is on paper, it's probably easiest to use the slope-intercept form, y equals mx plus b. So we'll probably have to rearrange the equations. In other words, x plus y equals 350 has to be changed into y equals minus x plus 350. And 45x plus 65y equals 18,750 has to be solved for y as well. And you can see there's a couple steps involved in doing that. Dividing by 65 and then reducing the fractions. And then finally, after we graph those lines, we'll find the x-y coordinate where the lines cross. This is going to give you the x and y values that solve the system. In other words, the number of tickets for each price level. For the graphical solution, there are going to be three possible outcomes. The first is that the lines are going to cross at one point. This gives us a unique solution, which is good. This means we can find a value of x and y, a single value of x and a single value of y that makes the equations both true. If the lines are parallel, they never cross and we don't have a solution. And finally, if the lines turn out to be the same lines, all the values of x and y along the lines are going to work, meaning there's an infinite number of solutions and there is no single unique solution. One problem with the graphical solution is that the accuracy of your solution is only as good as the graph that you make. For example, for the ticket problem, here's a graph. Now, it appears that the solution is 200, 150. So we might say that x is 200 and y is 150. But do we really know for sure that these are the exact numbers? It might be kind of hard to tell from the graph. So let's look at a couple other ways to do this and get a more accurate result. The first method is called substitution. When we solve by substitution, you're going to solve one of the equations for either x or y, and then substitute that expression into the other equation. This is going to result in one equation in one variable, which you will then solve. The value of the variable you just found is then substituted back into the first equation to get the value of the other variable. So this all sounds very confusing, and it is a little tedious, so let's go through an example. Let's solve the system x plus y equals 1, which we'll call equation 1, and 2x plus y equals 1, which we'll call equation 2. From equation 1, we're going to subtract x from both sides in order to solve for y. This gives us y equals 1 minus x. We're going to put that expression in place of y in equation 2. So instead of 2x plus y equals 1, we'll have 2x plus 1 minus x equals 1. We're going to solve equation 2 since now we have one equation with one variable. We take 2x plus 1 minus x equals 1. That's going to reduce to x plus 1 equals 1. Subtracting 1 from both sides, we get x equals 0. This is our solution for x. Now we're going to take that number and put it back into equation 1. And notice that when we subtracted x from both sides of equation 1, we got a version of equation 1, which is y equals. We can use that version of the equation, substituting x equals 0, to get our value of y directly. So in other words, y equals 1 minus x. We'll substitute 0 for x, giving us y equals 1 minus 0, which means y equals 1. So our solution is x equals 0, y equals 1. The second method algebraically is called elimination. When we do this method, we end up multiplying both sides of one equation by some number that eliminates one of the variables when the two equations are added together. We solve the resulting equation for the remaining variable, much like we did in substitution. And also like substitution, we put that answer back into either of the original equations to find the other variable's value. So let's do an example of elimination. We use the same system that we did for substitution so we can compare the answers. First thing we'll do is multiply equation 1 by negative 2. Now why did we choose negative 2 and why did we choose equation 1? The choice of equation really doesn't matter, but the choice of the number should be some number that allows you to cancel the x in one equation with the x in the other, or the y in one equation with the y in the other. In this case, I'm going to try to cancel the 2x in equation 2 with the minus 2x in the modified or multiplied equation 1. So here's equation 1 after multiplying by negative 2. I'm going to add the original equation 2, and what I want to happen is for that negative 2x and the 2x to cancel and give me 0, leaving me just an expression in y. And so I get minus y equals minus 1, which I can solve as y equals 1. Now I can take that y value, and I'm going to go ahead and just put that back into equation 1. So instead of x plus y equals 1, I'm going to have x plus 1 equals 1. And the solution to that is x equals 0. So my solution for this system is x equals 0, y equals 1, which is the same as we had for the substitution method. And when all else fails, we'll go to the calculator. The Inspire's calculator screen has a function called LinSolve. This stands for Linear System Solver. It's accessed by pressing Menu, 3 for Algebra, and then 2, Solve System of Linear Equations. When you press that, you're going to get this screen. You can change the number of equations if you have more than 2, and if you want to change the names of the variables to match what you have on the problems, you have that option as well. When you get back to the calculator screen, you'll have the LinSolve template set up. All you need to do is to type in the equations exactly as you see them in your problem. There's no need to reformat, solve for y, or anything else like that. So here we have the ticket problem that we started the presentation with. X plus y equals 350 and 45x plus 65y equals 18,750. Press enter and you get your solution. Now when we did this graphically, we thought that the answer might be x equals 200, y equals 150, but the graph was not necessarily accurate enough to really read down to the level of precision that we might want. Here we've actually verified through the calculator that indeed x equals 200, y equals 150 is the correct solution. Now, if you recall, there's three possible outcomes for any system of linear equations, and it's possible then that you could have three different results from LinSolve, and let's look at how these look so you'll know what to look for. First of all, if you have one unique solution, that means you do have a value of x and a value of y that gives you a solution to both equations. You're going to have two numbers come out in the brackets. That tells you that you do have the unique solution. If you have something like you have in the middle here on the screen, 1 minus c1 or something that's got this c1 or something else like that in there, what that basically means is that you have an infinite number of solutions. This is where you have two lines that are the same line. They overlap. And then at the very end here, if it says no solution found, well, that's exactly what happens. You have two parallel lines in this case, and so they never cross, and you never have a solution.